Predicting physical reality is a calculation-heavy task. If you try to model the aerodynamic stress across a descending airplane wing, you are immediately confronted by thousands of turbulent variables, invisible waves of pressure overlapping and interfering with each other across every inch of metal. To manage this chaos, physicists rely on a mathematical tool known as a Green's function. Because this tool is a staple in fluid and acoustic dynamics, it is often misunderstood. Many assume the Green's function is a wave equation, a mathematical object that possesses a wavy, oscillating shape by definition. This misses the mechanics of the tool. To use it correctly, we have to look past the name and see how it actually models the universe. A Green's function is a pure point response tool. It functions as the mathematical footprint of a single idealized action. It is a blank building block. It carries no predefined physical shape and contains no built-in wave-like behavior. The actual shape of a Green's function is determined by the rules of the system we place it inside, not the tool itself. To isolate a clean input, we use the multiplied delta function. The first half, the spatial component, acts as a filter, selecting a single coordinate in space. The second half, the temporal component, narrows the timeline down to one exact instant. By combining these constraints, we create a source concentrated at one precise space-time coordinate, a reference point used to test any physical rule. In this context, the physical rule is the governing equation, or PDE. This equation dictates how a system reacts to our point input. For a static problem, the equation applies constant pressure. The beam deforms, but doesn't move through time. Its shape is fixed. Add inertia for a dynamic problem, and the rule changes. Like a sharp hammer strike, the disturbance now propagates outward as traveling ripples. It is the dynamic nature of the rule, not the Green's function itself, that creates this traveling, wave-like appearance. The Green's function simply inherits its behavior from the governing PDE. It can describe a static bend, a diffusing heat cloud, or a traveling wave as required. We also have to account for physical boundaries. If a wave is trapped inside a finite box, the mathematical tools we use to solve the equations must adapt to those limits. These are Dirichlet boundary conditions. They represent the physical reality that the wave's energy must be zero at the fixed walls of the container. Because the wave is constrained at the ends, we decompose the space using a Fourier sine series. These sine waves are the natural basis here because they always hit zero at the boundaries. This sine series is the method we use to represent the shape of the solution. It's a separate step from the residue theorem, a complex analysis tool used later to actually compute the values of the resulting integrals. By selecting a mathematical basis that matches our physical boundaries, we can build a Green's function for any specific localized environment. But how does a single point response explain the complex, overlapping waves we see in the real world? The answer is this integral representation formula. It shows that the total response, U, is the sum of every microscopic point response, G, weighted by the actual source input, F. This is the command for superposition. We multiply every point source by its specific Green's function and then add the results together. When thousands of these individual point responses overlap, they merge. These tiny, localized impacts combine to form a single, unified event. The complex physical reality we observe is the sum of these simple, localized responses. This is why the Green's function is so effective. It allows us to analyze the behavior of the universe one infinitesimal point at a time. By solving for a single point in spacetime and applying the principle of superposition, we can build back the complete picture of how any system behaves.